In physics, fluid dynamics is a subdiscipline of fluid mechanics that deals with fluid flow, the natural science of fluids in motion. It has several subdisciplines itself, including aerodynamics and hydrodynamics. Fluid dynamics has a wide range of applications, including calculating forces and moments on aircraft, determining the mass flow rate of petroleum through pipelines, predicting weather patterns, understanding nebulae in interstellar space, and modeling fission weapon detonation. Some of its principles are even used in traffic engineering, where traffic is treated as a continuous fluid, and crowd dynamics. Fluid dynamics offers a systematic structure, which underlies these practical disciplines, that embraces empirical and semi-empirical laws derived from flow measurement and used to solve practical problems. The solution to a fluid dynamics problem typically involves calculating various properties of the fluid, such as flow velocity, pressure, density, and temperature, as functions of space and time. Before the 20th century, hydrodynamics was synonymous with fluid dynamics. This is still reflected in names of some fluid dynamics topics, like Magnetohydrodynamics and hydrodynamic stability, both of which can also be applied to gases. Equations of fluid dynamics. The foundational axioms of fluid dynamics are the conservation laws, specifically, conservation of mass, conservation of linear momentum, and conservation of energy. These are based on classical mechanics and are modified in quantum mechanics and general relativity. They are expressed using the Reynolds transport theorem. In addition to the above, fluids are assumed to obey the continuum assumption. Fluids are composed of molecules that collide with one another and solid objects. However, the continuum assumption considers fluids as continuous, rather than discrete. Consequently, properties such as density, pressure, temperature, and flow velocity are assumed well-defined at infinitesimally small points, and are assumed to vary continuously from one point to another. The fact that the fluid is made up of discrete molecules is ignored. For fluids that are sufficiently dense to be a continuum, do not contain ionized species, and have flow velocities small in relation to the speed of light. The momentum equations for Newtonian fluids are the Navier-Stokes equations, which is a nonlinear set of differential equations that describes the flow of a fluid whose stress depends linearly on flow velocity gradients and pressure. The unsimplified equations do not have a general closed-form solution, so they are primarily of use in computational fluid dynamics. The equations can be simplified in a number of ways, all of which make them easier to solve. Some of them allow appropriate fluid dynamics problems be solved in closed form. In addition to the mass, momentum, and energy conservation equations, a thermodynamical equation of state giving the pressure as a function of other thermodynamic variables for the fluid is required to completely specify the problem. An example of this would be the perfect gas equation of state, where P is pressure, ρ is density, ρ is the gas constant, m is molar mass, and T is temperature. Conservation laws. 3 conservation laws are used to solve fluid dynamics problems, and may be written in integral or differential form. Mathematical formulations of these conservation laws may be interpreted by considering the concept of a control volume. A control volume is a specified volume in space through which air can flow in and out. Integral formulations of the conservation laws consider the change in mass, momentum, or energy within the control volume. Differential formulations of the conservation laws apply Stokes' theorem to yield an expression which may be interpreted as the integral form of the law applied to an infinitesimal volume at a point within the flow. Mass continuity. The rate of change of fluid mass inside a control volume must be equal to the net rate of fluid flow into the volume. Physically, this statement requires that mass is neither created nor destroyed in the control volume, and can be translated into the integral form of the continuity equation. Above is the fluid density, u is the flow velocity vector, and t is time. The left-hand side of the above expression contains a triple integral over the control volume, whereas the right-hand side contains a surface integral over the surface of the control volume. The differential form of the continuity equation is, by the divergence theorem, conservation of momentum. This equation applies Newton's second law of motion to the control volume, requiring that any change in momentum of the air within a control volume be due to the net flow of air into the volume and the action of external forces on the air within the volume. In the integral formulation of this equation, body forces here are represented by F body, the body force per unit mass. Surface forces, such as viscous forces, are represented by the net force due to stresses on the control volume surface. The differential form of the momentum conservation equation is as follows. Here, both surface and body forces are accounted for in one total force. For example, F may be expanded into an expression for the frictional and gravitational forces acting on an internal flow. In aerodynamics, air is assumed to be a Newtonian fluid, which posits a linear relationship between the shear stress and the rate of strain of the fluid. The equation above is a vector equation. In a three-dimensional flow, it can be expressed as three scalar equations. The conservation of momentum equations for the compressible, viscous flow case are called the Navier-Stokes equations. Conservation of energy. Although energy can be converted from one form to another, the total energy in a given closed system remains constant. Above, H is enthalpy, K is the thermal conductivity of the fluid, T is temperature, and is the viscous dissipation function. The viscous dissipation function governs the rate at which mechanical energy of the flow is converted to heat. The second law of thermodynamics requires that the dissipation term is always positive. Viscosity cannot create energy within the control volume. The expression on the left side is a material derivative. However, in many situations the changes in pressure and temperature are sufficiently small that the changes in density are negligible. In this case the flow can be modeled as an incompressible flow. Otherwise the more general compressible flow equations must be used. Mathematically, incompressibility is expressed by saying that the density ρ of a fluid parcel does not change as it moves in the flow field, i.e., where dt is the substantial derivative, which is the sum of local and convective derivatives. This additional constraint simplifies the governing equations, especially in the case when the fluid has a uniform density. For flow of gases, to determine whether to use compressible or incompressible fluid dynamics, the Mach number of the flow is evaluated. As a rough guide, compressible effects can be ignored at Mach numbers below approximately 0.3. For liquids, whether the incompressible assumption is valid depends on the fluid properties and the flow conditions. Acoustic problems always require allowing compressibility, since sound waves are compression waves involving changes in pressure and density of the medium through which they propagate. In viscid versus Newtonian and non-Newtonian fluids, all fluids are viscous, meaning that they exert some resistance to deformation. Neighboring parcels of fluid moving at different velocities exert viscous forces on each other. The velocity gradient is referred to as a strain rate. It has dimensions. Isaac Newton showed that for many familiar fluids such as water and air, the stress due to these viscous forces is linearly related to the strain rate. Such fluids are called Newtonian fluids. The coefficient of proportionality is called the fluid's viscosity. For Newtonian fluids, it is a fluid property independent of the strain rate. Non-Newtonian fluids have a more complicated, non-linear, stress-strain behavior. The subdiscipline of rheology studies the stress-strain behaviors of these fluids, which include emulsions and slurries. Some viscoelastic materials such as blood and some polymers, and sticky liquids such as latex, honey and lubricants. The dynamic of fluid parcels is described with the help of Newton's second law. An accelerating parcel of fluid is subject to inertial effects. The Reynolds number is a dimensionless quantity which characterizes the magnitude of inertial effects compared to the magnitude of viscous effects. A low Reynolds number indicates that viscous forces are very strong compared to inertial forces. In such cases, inertial forces are sometimes neglected. This flow regime is called Stokes or creeping flow. On the contrary, high Reynolds numbers indicate that the inertial effects have more effect on the velocity field than the viscous effects. In high Reynolds number flows, the flow is often modeled as an inviscid flow, an approximation in which viscosity is completely neglected. The Navier-Stokes equations then simplify into the Euler equations. Integrating these along a streamline in an inviscid flow yields Bernoulli's equation. When in addition to being inviscid, the flow is everywhere irrotational, Bernoulli's equation can be used throughout the flow field. Such flows are called potential flows because the velocity field may be expressed as the gradient of a potential. This idea can work fairly well when the Reynolds number is high. However, problems such as those involving solid boundaries may require that the viscosity be included. Viscosity cannot be neglected near solid boundaries because the no-slip condition generates a thin region of large strain rate, the boundary layer, in which viscosity effects dominate and which thus generates vorticity. Therefore, to calculate net forces on bodies, viscous flow equations must be used. Inviscid flow theory fails to predict drag forces, a limitation known as the D'Alembert's paradox. A commonly used model, especially in computational fluid dynamics, is to use two flow models. The Euler equations away from the body, and boundary layer equations in a region close to the body. The two solutions can then be matched with each other, using the method of matched asymptotic expansions. Steady versus unsteady flow. When all the time derivatives of a flow field vanish, the flow is considered steady flow. Steady-state flow refers to the condition where the fluid properties at a point in the system do not change over time. Otherwise, flow is called unsteady. Whether a particular flow is steady or unsteady can depend on the chosen frame of reference. For instance, laminar flow over a sphere is steady in the frame of reference that is stationary with respect to the sphere. In a frame of reference that is stationary with respect to a background flow, the flow is unsteady. Turbulent flows are unsteady by definition. A turbulent flow can, however, be statistically stationary. According to Pope, the random field U is statistically stationary if all statistics are invariant under a shift in time. This roughly means that all statistical properties are constant in time. Often, the mean field is the object of interest, and this is constant too in a statistically stationary flow. Steady flows are often more tractable than otherwise similar unsteady flows. The governing equations of a steady problem have one dimension fewer than the governing equations of the same problem without taking advantage of the steadiness of the flow field. Laminar versus turbulent flow. Turbulence is flow characterized by recirculation, eddies, and apparent randomness. Flow in which turbulence is not exhibited is called laminar. It should be noted, however, that the presence of eddies or recirculation alone does not necessarily indicate turbulent flow. These phenomena may be present in laminar flow as well. Mathematically, turbulent flow is often represented via a Reynolds decomposition, in which the flow is broken down into the sum of an average component and a perturbation component. It is believed that turbulent flows can be described well through the use of the Navier-Stokes equations. Direct numerical simulation, based on the Navier-Stokes equations, makes it possible to simulate turbulent flows at moderate Reynolds numbers. Restrictions depend on the power of the computer used and the efficiency of the solution algorithm. The results of DNS have been found to agree well with experimental data for some flows. Most flows of interest have Reynolds numbers much too high for the DNS to be a viable option. Given the state of computational power for the next few decades, Any flight vehicle large enough to carry a human, moving faster than 72 km per hour is well beyond the limit of DNS simulation. Transport aircraft wings have Reynolds numbers of 40 million. Solving these real-life flow problems requires turbulence models for the foreseeable future. Reynolds averaged Navier-Stokes equations combined with turbulence modeling provides a model of the effects of the turbulent flow. Such a modeling mainly provides the additional momentum transfer by the Reynolds stresses, although the turbulence also enhances the heat and mass transfer. Another promising methodology is large eddy simulation, especially in the guise of detached eddy simulation, which is a combination of RANS turbulence modeling and large eddy simulation. Subsonic versus transonic, supersonic and hypersonic flows. While many terrestrial flows occur at low Mach numbers, many flows of practical interest occur at high fractions of the Mach number m equals 1 or in excess of it. New phenomena occur at these Mach number regimes, and it is necessary to treat each of these flow regimes separately. Magnetohydrodynamics. Magnetohydrodynamics is the multidisciplinary study of the flow of electrically conducting fluids in electromagnetic fields. Examples of such fluids include plasmas, liquid metals, and salt water. The fluid flow equations are solved simultaneously with Maxwell's equations of electromagnetism. Other approximations. There are a large number of other possible approximations to fluid dynamic problems. Some of the more commonly used are listed below. The Boussinesq approximation neglects variations in density except to calculate buoyancy forces. It is often used in free convection problems where density changes are small. Lubrication theory and Heald-Shor flow exploits the large aspect ratio of the domain to show that certain terms in the equations are small and so can be neglected. Slender body theory is a methodology used in Stokes flow problems to estimate the force on, or flow field around, a long slender object in a viscous fluid. The shallow water equations can be used to describe a layer of relatively inviscid fluid with a free surface, in which surface gradients are small. The Boussinesq equations are applicable to surface waves on thicker layers of fluid and with steeper surface slopes. Darcy's law is used for flow in porous media, and works with variables averaged over several pore widths. In rotating systems, the quasi-geostrophic equations assume an almost perfect balance between pressure gradients and the Coriolis force. It is useful in the study of atmospheric dynamics. Terminology in fluid dynamics. The concept of pressure is central to the study of both fluid statics and fluid dynamics. A pressure can be identified for every point in a body of fluid, regardless of whether the fluid is in motion or not. Pressure can be measured using an aneroid, Bourdon tube, mercury column, or various other methods. Some of the terminology that is necessary in the study of fluid dynamics is not found in other similar areas of study. In particular, some of the terminology used in fluid dynamics is not used in fluid statics. Terminology in incompressible fluid dynamics. The concepts of total pressure and dynamic pressure arise from Bernoulli's equation and are significant in the study of all fluid flows. To avoid potential ambiguity when referring to pressure in fluid dynamics, many authors use the term static pressure to distinguish it from total pressure and dynamic pressure. Static pressure is identical to pressure and can be identified for every point in a fluid flow field. In aerodynamics, L.J. Clancy writes, to distinguish it from the total and dynamic pressures, the actual pressure of the fluid, which is associated not with its motion but with its state, is often referred to as the static pressure, but where the term pressure alone is used it refers to this static pressure. A point in a fluid flow where the flow has come to rest is of special significance. It is of such importance that it is given a special name, a stagnation point. The static pressure at the stagnation point is of special significance and is given its own name, stagnation pressure. In incompressible flows, the stagnation pressure at a stagnation point is equal to the total pressure throughout the flow field. Terminology in compressible fluid dynamics. In a compressible fluid, such as air, the temperature and density are essential when determining the state of the fluid. In addition to the concept of total pressure, the concepts of total temperature and total density are also essential in any study of compressible fluid flows. To avoid potential ambiguity when referring to temperature and density, many authors use the terms static temperature and static density. Static temperature is identical to temperature, and static density is identical to density, and both can be identified for every point in a fluid flow field. The temperature and density at a stagnation point are called stagnation temperature and stagnation density. A similar approach is also taken with the thermodynamic properties of compressible fluids. Many authors use the terms total enthalpy and total entropy. The terms static enthalpy and static entropy appear less common, but where they are used they mean enthalpy and entropy respectively, using the prefix static to avoid ambiguity with their total or stagnation counterparts. Because the total flow conditions are defined by isentropically bringing the fluid to rest, the total entropy is by definition always equal to the static entropy.